Hello, everybody. This is Miss Peachy from WCA Physics, and I'm going to do another little video short today, and we're going to talk a little bit about displacement with constant acceleration. So just when you're looking at how some of these terms are related to each other that we've been talking about in the last several videos here, think about how displacement is going to depend upon acceleration, how fast something starts out, and time. So these are all important factors in how much displacement actually takes place. So I'm going to put those on here. These are key here. So acceleration, initial velocity, and time. So when you want to figure out like how much displacement has occurred, these three factors are key pieces of information. How much displacement has occurred. All right. So let's kind of look at a couple of different things. Let's look at some of the formulas that we've been talking about and kind of look at alternate ways in which we can view those formulas. So velocity, average velocity, we've talked about this before, is delta x over delta t, right? So change in displacement over change in time. And we can also say that if acceleration is constant, so if acceleration is constant, that let's look at a graph, for example. I'm going to show you a little graph here with velocity on the y-axis and time on the x-axis. So I'm going to draw a straight line, which indicates constant acceleration. Here we have our initial spot, our starting point, v sub I. And we have our final velocity, v sub f. We can say that the average velocity is right in the middle. Okay? We can mathematically express this as velocity average is equal to v sub I plus v sub f divided by 2. This only works with constant acceleration. Though if this was a curve, we couldn't use this. So what we can do then is we can set this expression of average velocity equal to this expression of average velocity. Delta x over t, delta t, equals v sub I plus v sub f over 2. And now I can kind of solve for delta t. If I'm solving for delta t, I'm going to multiply the left side by delta. I'm solving for delta x. So I'm going to multiply the left side by delta t, kind of move it over here, right? When I do that, I end up with delta x equals, and I'm going to pull this out here and call this 1/2 times v sub I plus v sub f, because it's the same thing, times delta t. So this is a different expression. So now what this tells me is that I can tell how much displacement has taken place if I know what the starting velocity was, what the final velocity is, and how long of a period of time has passed. Right? So this is an equation. This is one derivation of an equation using like the accelerations, using velocity and displacement, and being able to kind of solve for delta t here. So let's do an example problem using this derivation here. In this example problem, a race car reaches a speed of 42 meters per second and then begins a uniform negative acceleration using its parachute and braking system and comes to a rest 5.5 seconds later. Find the distance the car traveled during braking. So let me just say that to you one more time. A race car reaches a speed of 42 meters per second and then begins a uniform negative acceleration using its parachute and braking system and comes to a rest 5.5 seconds later. Find the distance the car travels during braking. So we're starting essentially this at the moment the brakes are applied. So we don't really care about what happened prior to when it was racing. It's now traveling at 42 meters per second and then it starts to brake, right? So our givens here. Our initial velocity is 42 meters per second. Final velocity, well, it's braking, so it's going to end up at 0 meters per second. It takes 5.5 seconds to do this, and we want to know how far it traveled. We don't know delta x here. Okay, so it's really a fairly simple problem. This is kind of what I call plug and play physics. When you are given one equation and you just need to plug numbers in to solve for that equation. So let's do it. Let's plug some numbers in. Let's do some plug and play. It's the easy stuff. So delta x is equal to 1/2 v sub I plus v sub f times delta t. Right? That's our formula that we're going to use. Delta x is equal to 1/2 42 meters per second plus 0. Well, we don't really need to even add the plus 0, right? Times 5.5 seconds. Okay, so let's do 42 times 5.5. 231 and divide it by 2. 115.5. And then our units, remember, meters per second times seconds. Well, seconds will cancel. So we'll end up with just meters. Okay, and now, this is the answer here. I will tell you that since you're using 42 here, so the ones place is your kind of like your significant digits here, that's kind of what we should report the answer to here. So we'll just round this to the nearest whole number. Okay. So there you go. Pretty simple problem in that situation. Now you can also look at other ways or other derivations, excuse me, other equations. And a derivation is just basically where you take one equation and you kind of maybe take more than one equation and combine them to make a new equation from that. Okay. Actually, that's kind of the opposite of a derivation, but a derivation would be when I take an equation and I tell you how we came up with that equation, but I'm kind of showing you that in this situation. So another thing we can look at is final velocity depends on initial velocity, acceleration, and time. This is another relationship. So final velocity well, what's really important here? We need to know the initial velocity. We need to know the acceleration, the rate of acceleration. And we need to know how much time has passed. Those are all really key factors. Remember, acceleration is written as delta v over delta t. So that's another way of saying that is v sub f minus v sub I over t sub f minus t sub I. Whew. I don't know if you guys can hear that, but it's like really windy today, right? So I can rewrite this I'm actually going to just keep that as delta t at the bottom. Okay, so we'll do v sub f minus v sub I over delta t. We'll make it simplify it just for the math's sake. All right, so I want to get rid of that on the denominator. So I'm just going to multiply both sides times delta t. And so I get a delta t equals v sub f minus v sub I. And I really want to know what our final velocity, that's the thing I was looking for, remember? So I'm going to add v sub I to both sides. A delta t plus v sub I is equal to v sub f. So if I want to know final velocity, if I take the acceleration times the time, the change in time, and add the initial velocity, I should calculate the final velocity. So there you go. That's another kind of equation we can get by using some other equations in there. Okay, so what you can do next is we can actually take this and we can take the last equation that we constructed. If I can get back to that sheet. This is, like I said, so high tech, ladies and gentlemen. Okay, we can take this equation, right? And so this is delta x. And we can substitute this in. Or I should say we could substitute this in here. So take out this v sub f and substitute this equation, a delta t plus v sub I, in for v sub f here. It gets a little complicated, people. Let me show you. All right. So it's delta x equals 1/2 v sub I plus v sub f all over delta t. Okay. And then what I want to do is take this thing out, put that in its place. So delta x equals 1/2 v sub I plus, I'm just going to flip that around to make it easier, plus v sub I plus a delta t, like that. Then I can combine these two guys. Delta x equals 1/2 2 v sub I Oh, I forgot my delta t on the outside, sorry. Plus a delta t. And then I can multiply through by delta t. And so you end up with delta x equals 1/2 2 v sub I plus a delta t squared. Okay, and then you can take this equation here and you can monkey around with it a bit more. Because you can distribute this 1/2 through, take 1/2 of 2 is 1, right? So these guys kind of cancel. And then this 1/2 here becomes 1/2. So ultimately, the final equation is delta x equals v sub I delta t plus 1/2 a delta t squared. So another way which you can solve for your change in position by looking, if you have your initial velocity and you know how much time has passed and you know the acceleration, you can solve for change in position. Maybe you don't know your final velocity, but you know all this stuff instead. So these are all different, just basically different ways we're just monkeying with the same relationship, right? And we can use kind of one of those little derivations to be able to determine what's going on. Okay, there's a bunch of them, and I don't want to go through all of them because it's kind of boring. But let's see, I gave you 3, right? There's really just one more. And you have to just take my word for it. I'm not going to go through the whole thing again because, again, it gets kind of boring. But you can, if you can solve for final velocity but you're actually getting v sub f squared equals initial velocity squared plus 2ax. Or, sorry, it should be delta x. Poop. There we go. It's a delta x. So if you know your initial velocity and the acceleration, and the displacement, but you don't know the time, this is the equation you want to use, right? So if you don't know the time, this is this equation you want to use. So I'm going to show you a page. This is actually from a textbook here, and I'm going to show you this because it's a great chart right here, and this is something you're going to want to know. These are called your kinematic equations for straight line motion. I'm going to scooch this over and kind of focus in a little bit so you can see it a bit better. There, it was clear for a second. There we go. So these are the ones we just went through right here on the left side. Whoops. Do you love my technology? Those are the ones we just went through. So you can solve any acceleration problem if you're looking for change in position, you know initial and final velocity and time, use equation 1. If you know, you don't know the acceleration, but you don't know the final velocity, you can use equation 2. If you know the initial velocity, the acceleration and time, but you need to know the change in position, use equation 3. And for equation 4, you don't know time. So sometimes you need to use more than one of these because you need to be able to solve multiple parts. On the right is just if you start from rest, your initial velocity is always going to be 0. So in those situations, they're just simplified for when you start from rest. So I would screenshot this if you can, and then you can actually save a copy of these. I also have these in the study guide for Unit 1. So if you look at the study guide for the Unit 1 test, there's actually a picture of that chart right in there. All right, so we went through some of the equations in this video. We didn't really go through that many examples of the actual equations. How did we come up with the equations, but not really how to use them. So we'll be seeing more how to use those equations when we get into some of the stuff on free fall, which is in the next video. So hopefully that helped you guys. If you have any questions, send me an email and I'll be happy to answer them.